Hello everyone. This is the fifth class on the mechanics of solids. In this class, we will study the experiments to determine Young's modulus of the material of a beam using pin and microscope method. We will study three experiments. One is cantilever, the second is uniform bending, and the third is non-uniform bending. First, let us study cantilever. How to determine Young's modulus of the material of a beam using cantilever. Before going to the experimental part, let us revise cantilever. What is a cantilever? A thin uniform rod clamped horizontally at one end and loaded at the other is called a cantilever. Because of this loading, the free end of the cantilever undergoes a depression delta. Before loading, the position of the beam is B, and after loading, the free end deflect to B dash. So the cantilever has a depression delta. Now for a rectangular bar, this delta is given by W 4W L cube divided by Y BD cube, where W is equal to mg. W is equal to mg. L is the length of the rod between the fixed end and the loaded end. Y is the Young's modulus of the material of a beam. B is the breadth of the beam. D is the thickness of the beam. In the experiment, we will determine the depression at the free end of the cantilever delta using a traveling microscope. That is by pin and microscope method. We will determine the value of the depression delta. Once we determine delta, we can find out Young's modulus using the formula 4mg L cube divided by BD cube delta. This is the experimental arrangement. The given beam is rigidly clamped at one end. A weight hanger is suspended at a point near to the free end of the beam. Now a pin is fixed vertically at this point. The weight hanger is arranged at the free end of the beam and a pin is fixed vertically at this point. There is a traveling microscope which is focused onto the tip of the pin. There is a traveling microscope which is focused onto the tip of the pin. Initially, the bar is brought to the elastic mode by loading and unloading the hanger few times. By loading and unloading the hanger few times, bring the bar into elastic mode. Now with weight W0 alone, the microscope is adjusted so that the horizontal crosswire coincide with the tip of the pin. What is the weight of the weight hanger? We will say it is the dead load W0. With this dead load W alone, the microscope is adjusted so that the horizontal crosswire of the microscope coincide with the tip of the pin. When you look through the traveling microscope, the tip of the pin looks as shown in figure. Now adjust the traveling microscope in such a way that the horizontal crosswire coincides with the tip of the pin. This is the horizontal crosswire and that should coincide with the tip of the pin. Now measure the reading. Now note the readings on the vertical scale of the microscope. Load the weight hanger, look through the traveling microscope, and adjust the microscope such that the horizontal crosswire coincide with the tip of the pin. Now the readings on the vertical scale of the microscope is noted. This is the vertical scale on the microscope. Vertical scale of the microscope is shown in the left side. In the present case, the MSR, the main scale reading is 9.15, corresponding to this dead load W0, and the VSR is 7. Least count of this traveling microscope is 0.001 centimeter. Therefore, the total reading corresponding to this particular case is MSR plus VSR into LC, that is 9.15 plus 7 into 0.001, that is 9.157 centimeter. Now write the reading 9.157 in the loading column corresponding to the dead load W0. Now after that, a weight of 1 m is added on the weight hanger so that the total weight is W0 plus 1 m. Add a weight 1 m so that the total weight is W0 plus 1 m. Then the microscope is adjusted so that the horizontal crosswire coincide with the tip of the pin and not the reading corresponding to W0 plus 1 m. Now add a mass 1 m again. So the total weight is W0 plus 2m. Then the microscope reading is noted. The microscope is adjusted so that the horizontal crosswire of the microscope coincide with the tip of the pin, and then note the corresponding reading and write it in the column. Now add a weight W0 plus 3m. The microscope reading is noted and write the corresponding reading in the loading column. Corresponding reading in the loading column. Then again add 1 m weight into the weight hanger. So the total weight is W0 plus 4m. Then the readings on the vertical scale of the microscope is again noted and write the corresponding reading on the loading column. Then add one more weight. So the total weight is W0 plus 5m. Then again the readings on the vertical scale of the microscope is noted. As in the previous case, now write the corresponding reading on the loading column. Now we are going to unload the weight. So first write the same reading, that is W0 plus 5m on the unloading column. First write the same reading of W0 plus 5m on the unloading column. Then remove 1 m from the weight hanger. Then remove 1 m from the weight hanger so that the total weight become W0 plus 4m. Now the microscope is adjusted so that the horizontal crosswire coincide with the tip of the pin, and write the reading corresponding to W0 plus 4m in the unloading column. Then remove 1 m again, so the total weight become W0 plus 3m. Now that the traveling microscope reading is noted, and write the corresponding reading in the unloading column. Then remove one more weight, so the total weight is W0 plus 2m. The traveling microscope reading is again noted. Now write the reading corresponding to W0 plus 2m again. Now remove 1m again. So the total weight become W0 plus 1m. Note the readings on the traveling microscope, and these readings are noted. Finally, remove that 1m. So the weight is actually the weight of the weight hanger only. Weight is actually the weight of the weight hanger only. Now note the corresponding reading and write the corresponding reading of W0 in the unloading column. Now take the mean value of the reading. Once you have loading and once you have unloading, write the corresponding mean value. The mean value of the reading corresponding to W0 is R0, W0 plus 1m is R1, W0 plus 2m is R2, W0 plus 3m is R3, and the mean value corresponding to W0 plus 4m is R4, and the mean value corresponding to the W0 plus 5m is R5. Now let us find out the depression for a load 3m. Now let us find out the depression for a load 3m. So we have the reading corresponding to W0, W0 plus 1m, 2m, 3m, 4m and 5m. Now our aim is to find out the depression for a load 3m. How much the tip deflects for a load of 3m. That is the depression for a load 3m. How we find out the depression for a load 3m? Just subtract the value of W0 plus 3m and W0. That is, subtract R0 from R3. If you subtract R0 from R3, you will get a depression for a load 3m. Similarly, if you subtract R1 from R4, then again you will get a depression for a load 3m. Also, if you subtract R2 from R5, you will again get the depression for a load 3m. That is, we are getting 3 readings that all corresponding to the depression for a load 3m. Now take the average of these 3 readings. When you take the average of these 3 readings, this will give the depression for a load 3m. Once you have the depression for a load 3m, you can find out the mean depression for a load m. Divide the readings again by 3. Divide the depression for a load 3m by 3. Then you will get the depression for a load m. That is given by delta. The depression for a load m, that is given by delta. Once you find out delta, what is delta? It is a depression for a load m. Then find the breadth of the bar using vernier caliper. Find the breadth of the bar using vernier caliper. Then the thickness of the beam using screw gauge. Then find out the thickness of the beam using screw gauge. Determine the breadth of the bar using vernier caliper and the thickness of the bar using screw gauge. So you will get B and D. Once we have delta, B and D, then you can find out the Young's modulus of the material of the bar using the formula Y is equal to 4 mg L cube divided by BD cube delta. Y is equal to 4 mg L cube divided by BD cube delta, where m is the mass. Here it is 50 gram. This is the experimental technique to determine the Young's modulus of the material of the beam using cantilever. Hello everyone. Let us discuss the second experiment to determine The Young's modulus of the material of a beam using pin and microscope method, that is non-uniform bending. Before going to the experimental section, let us briefly revise what is meant by non-uniform bending. In non-uniform bending, the beam is supported at its ends and loaded at the middle. The beam is supported at its ends and loaded at the middle. AB is a rigid uniform beam resting symmetrically on two knife edges K1 and K2. L is the length of the beam, that is A and B are separated by a distance L. It is loaded at the middle point D with a load W is equal to mg. Now the reactions on each knife edge is W by 2 and that is acting vertically upwards. Now because of this loading, the beam will undergo bending as shown in the picture. Here the bending is not uniform. Here the bending is not uniform. Because of this bending, the central point D will undergo a depression delta. Because of this bending, the central point will undergo a depression delta and the depression is maximum at the central point. And we have seen that for a rectangular bar, the depression at the middle point is given by WL cube divided by 4BD cube Y, where B is the breadth of the beam, D is the thickness of the beam, and W is equal to mg. L is the length of the beam. In the present experiment, we will determine the depression at the middle point delta using a traveling microscope, and once we know delta, we can calculate the Young's modulus Y using the formula mgL cube divided by 4BD cube delta, where delta is a depression at the middle point that we can determine using a traveling microscope. This is the experimental arrangement for non-uniform bending. The given bar is symmetrically supported on two knife edges. The given bar is symmetrically supported on two knife edges at K1 and K2. A weight hanger having weight W0 is suspended from the center D of the beam. A pin is fixed vertically at this middle point D. There is a traveling microscope which is focused onto the tip of the pin. The traveling microscope is focused onto the tip of the pin such that the horizontal crosswire coincides with the tip of the pin. The horizontal crosswire and the tip of the pin is shown in this figure. This is the horizontal crosswire, and this horizontal crosswire should coincide with the tip. This is the tip of the pin. Initially, the beam is brought to elastic mode by loading and unloading the weight hanger in steps of few times. That is, by loading and unloading the weight hanger alone in several times, the beam is initially brought to elastic mode. Now, with the dead load alone, that is with the W0 alone, the readings on the vertical scale of the microscope is noted when the horizontal crosswire coincides with the tip of the pin. That is, with this dead load W0 alone, the readings of the traveling microscope is noted. Then add 1 m weight to the weight hanger, so the total weight is W0 plus 1 m. Then the readings on the vertical scale of the traveling microscope is noted. The horizontal crosswire must coincide with the tip of the pin, and if this is achieved, then note the reading and write the reading corresponding to W0 plus 1M. Now add one more weight in the weight hanger. So the total weight is W0 plus 2M. Now the readings on the traveling microscope is noted. Now write the reading corresponding to W0 plus 2M on the loading column. Now add one more weight, that is the total weight is W0 plus 3M in the weight hanger. Now the microscope is adjusted and note the reading corresponding to W0 plus 3M. Then add 1M again in the weight hanger. So the total weight is W0 plus 4M. Now the traveling microscope is adjusted and the readings on the vertical scale of the microscope is noted, and write the reading corresponding to W0 plus 4M. Now add one more weight. The total weight is W0 plus 5M. Note the reading on the traveling microscope and write the reading corresponding to W0 plus 5M in the tabular column. Now after that, let us unload the weight. So initially, write the same reading corresponding to W0 plus 5M in the unloading column. First reading is W0 plus 5M. Now weights are removed in steps and the readings are again noted. Weights are removed in steps and note the reading and record the reading in the tabular column corresponding to unloading. The readings are tabulated as in the previous experiment. Now we have loading and unloading. Let us take the mean value of loading and unloading. For W0, the mean value is R0. For W0 plus 1M, the mean value is R1. For W0 plus 2M, the mean value is R2. For W0 plus 3M, it is R3. For W0 plus 4M, it is R4. And for W0 plus 5M, it is R5. Once we have these readings, let us find out the depression for a load 3M. How much the middle point deflects corresponding to a load of 3M. To find the depression for a load 3M, take the difference R3 minus R0. If you take the difference R3 minus R0, that will corresponding to a depression for a load 3M. Similarly, R4 minus R1 will also corresponding to a depression for a load 3M. Similarly, R5 minus R2 will also corresponding to a depression for a load 3M. Thus, we have the depression for a load 3M. We have three readings corresponding to the depression for a load 3M. Now, let us take the average. And this average value gives the depression for a load 3M. We want the depression for a load M. How much the middle point deflect for a mass M. To get delta, divide the values that we are obtained in the previous column by 3. That is, depression for a load 3M divided by 3 gives depression for a load M delta. And after that, measure the breadth of the bar using vernier caliper and measure the thickness of the bar using screw gauge. Then we can find out the Young's modulus of the material of the beam using the equation Y is equal to mgl cube divided by 4bd cube delta, where m is the mass that we have added in each step. In the present case, it is 50 gram. This is the experimental method to determine Young's modulus of the material of the beam using non-uniform bending. Hello everyone. Our next experiment is uniform bending, let us study how uniform bending can be used to determine the Young's modulus of the material of a beam. Here also we will use the pin and microscope method. Before going to the experimental part, let us briefly revise uniform bending. Consider a beam of negligible mass supported symmetrically on two knife edges A and B in a horizontal level. A and B are two knife edges. Let the length AB be L. Now equal weights W are suspended from the beam at points C and D. Let AC is equal to P and BD is also equal to P. That is, equal weights are loaded at equal distances from the knife edge. Now, because of this kind of loading, because of this type of loading, the beam will bend, and the bent beam forms an arc of a circle with a constant radius of curvature. Therefore, the bending is uniform, and we will say the beam undergoes uniform bending. Because of this uniform bending, there is an elevation at the middle point of the beam. Now we have seen that for a rectangular bar, the elevation of the middle point delta is given by 3WP square divided by 2y BD cube, where W is equal to mg, P is the distance from the knife edge to the weight hanger, L is the length of the beam between two knife edges, and Y is the Young's modulus of the material of the beam, B is the breadth, and D is the thickness of the beam. Thus, if we know the elevation of the middle point delta, then we can determine the Young's modulus of the material of a beam. In the present case, we are determining the elevation of the middle point delta using a traveling microscope, and once delta is known, we can find out the Young's modulus Y of the beam using the relation 3 mgp L square divided by 2 BD cube delta. This is the experimental part of uniform bending. The given bar is supported symmetrically on two knife edges at A and B. There are two weight hangers. Two equal weight hangers are suspended. Two equal weight hangers are suspended at equal distances from the knife edge. Let the distance from the knife edge to the weight hanger be P. That is, in uniform bending, you have two weight hangers that are placed at equal distances from the knife edge. The distance between the knife edge is taken as L. A pin P is fixed vertically at the middle point of the beam. A pin is fixed vertically at the middle point of the beam. There is a traveling microscope which is focused onto the tip of the pin such that the horizontal crosswire coincides with the tip of the pin. The horizontal crosswire coincides with the tip of the pin. This is the horizontal crosswire, and this is the tip of the pin. The horizontal crosswire should coincide with the tip of the pin. Initially, the beam is brought to elastic mode by loading and unloading the weight hanger in steps of few times. Now, with dead load alone, that is with a W0 alone, the readings on the vertical scale of the microscope is noted. The readings on the vertical scale of the microscope is noted with the dead load W0 alone, and write the corresponding reading on the loading column corresponding to W0. Now add a weight 1m on each weight hanger. Add a weight 1m on each weight hanger. So the total weight is W0 plus 1m on each weight hanger. Now the readings on the vertical scale of the traveling microscope is noted, and write the reading corresponding to W0 plus 1m in the loading column. Now again add 1m weight in each weight hanger. So the total weight on each weight hanger is W0 plus 2m. W0 plus 2m. Now the readings are noted. Now add 1m again on the weight hanger. So the total weight is W0 plus 3m. Now the readings on the traveling microscope is noted, and write the reading corresponding to W0 plus 3m in the loading column. Now again add 1m on the weight hanger, on both weight hangers. So the total weight is W0 plus 4m on each weight hanger. Now the readings on the traveling microscope is noted. Now write the readings on the tabular column corresponding to W0 plus 4m. Now add one more weight. Now the weight on both weight hangers are W0 plus 5m. Now the readings on the traveling microscope is noted. So the readings on the vertical scale of the traveling microscope is noted, and write the corresponding reading on the loading column corresponding to W0 plus 5. Now let us unload the weight. To take the reading, first write the same reading for W0 plus 5m in the unloading column. Then the weights are removed in each step, and the readings of the traveling microscope is noted. The weights are removed in each steps, and the readings are again noted. So we have loading and unloading reading. Now take the mean value of loading and unloading. For W0, the mean value is R0. R1 is the mean value corresponding to W0 plus 1m. R2 is the mean value corresponding to W0 plus 2m in the loading and unloading. And R3 is the mean value corresponding to W0 plus 3m. For W0 plus 4m, the average value of loading and unloading is R4. And for W0 plus 5m, the average value of loading and unloading is R5. Our next aim is to find out the elevation for a load 3m. How much the tip of the beam is elevated for a load of 3m. Take R3 minus R0. It gives the elevation for a load 3m. Similarly, R4 minus R1 and R5 minus R2 will also give the elevation for a load 3m. So we have three readings corresponding to the elevation for a load 3m. Take the average so that we have the elevation for a load 3m. We need the elevation for a load m. So divide the readings that we have obtained in the previous column by 3. Elevation for a load 3m divided by 3 gives the elevation for a load m, that is delta. Now find the breadth of the bar using vernier caliper and the thickness of the bar using screw gauge. Once we have delta, B, D and L, we can calculate the Young's modulus of the material of the beam as Y is equal to 3 mgpl square divided by 2 BD cube delta, where m is the mass which we have added during loading. Delta is the elevation for a load m. This is the experimental method to determine the Young's modulus of a material of a beam using uniform bending.